Не, ну ладно, давайте на английском тогда, наверное, да? Можно начинать, да? Okay, I'll proceed in English. So, my talk is about triangulations of manifolds with small numbers of vertices. And to start with, I would like to start with explaining what kind of triangulations do I mean. I mean triangulations which are first simplicial complexes. This means that each simplex is uniquely determined by its vertices. We cannot have several simplexes with the same set of vertices. What does it? For instance, in theory of three manifolds, one often, well, I mean that it is prohibited for two simplexes to have, for instance, two common vertices without edge. This is not allowed. This is not simplicial complex, since we have two simplexes with the same set of vertices. This is not allowed. For instance, in theory of three manifolds, one often works with triangulations where such situations are allowed. This is another thing. Today I speak only on triangulations which are simplicial complexes. So this is not allowed. Is not allowed. Yes, the smallest triangulation in this sense is the boundary of tetrahedron. So of course one can consider other situations, but my point is this. This is first, and second, I want to work with PL triangulations of manifolds. This first, I start with explicit definition, and then I explain what this restriction means. Explicit definition is as follows. If I speak of a triangulation of d-dimensional manifold, so d is dimension, then for each vertex, I have the link of this vertex. Link is this complex such that the star of vertex is the cone of this link. So if this is vertex V, then this is link of V. And this link must be PL homeomorphic to the standard sphere, standard d-1 dimensional sphere, for instance, the boundary of the d-dimensional simplex. Why this restriction should be imposed? The matter is that there are very bad triangulations where this is not true. Namely, for instance, consider the Poincaré homology sphere or any other homology sphere. This is a nice, smooth three-dimensional manifold which has homology of the sphere, but which is not simply connected. So let us triangulate this manifold. Any smooth manifold can be triangulated. We have triangulation. There are explicit triangulation, for instance, with 16 vertices. So this is some very concrete example of simplicial complex. And then let us, I prefer to denote it by M. And now I would like to take the suspension over this triangulation. This is again a nice simplicial complex. So I just take two cones with the same base, and then the second suspension. So I take the second suspension over this homology sphere. And there is the famous double suspension theorem due to Edwards and Cannon, which says that this is homeomorphic to the usual sphere. This is by no means PL homeomorphic, but this is homeomorphic to 5-dimensional sphere. There is such fantastic, very strange fact. And this is not only for Poincare homology sphere, this is for any homology sphere. So what do we see? We see this object is a good simplicial complex. This is a triangulation of 5-dimensional sphere. But if we look on, these two suspensions, each suspension gives 2 vertices, and together they give the boundary of the square. So this is boundary of the square join with this initial M3. If we look on the link of this edge, then it is not a sphere at all. It is a homology sphere. It is exactly this M3. So this is very nasty type of triangulations. If we try to put these triangulations onto true sphere, then it would be wild. It would be widely embedded. It is a very bad object. So
the condition is imposed on vertex.
The condition is imposed on vertex, but the condition for links of all simplices is consequence of this. So it is true for all links that for all simplices that their links are also PL homeomorphic to the spheres of the corresponding dimensions. It is enough to require it for vertices, and it would be automatically true for all other simplices. But I need this condition because without it, we get to some wild objects. Okay, so this is object which I am going to work with, and now there is a rather interesting situation. Let us consider for any triangulation of a manifold, we can consider 2 parameters. D is dimension, and N is number of vertices. Well, okay, we have an obvious, I always consider only manifolds without boundary, compact manifolds without boundary. We have an obvious inequality that N should be at least D plus 2. Any D-dimensional simplex has at least D plus 1 vertices. And okay, we should have at least 1 vertex more to obtain a manifold without boundary. This bound is achieved for the boundary of the simplex. So this is obvious boundary. So it is one can consider such graph. I put D on this side and N on this, so we have this boundary. N equals D plus 2, and we have nothing here. And we have only boundaries of simplices on this slide. Yes, if we want to triangulate 1-dimensional manifold without boundary, then the simplest situation is the boundary of a triangle, since D is the dimension of my manifold. So in this situation, it's 1. Yes, of course, if I allow such things, I can get much smaller. And okay, but this is obvious. But an interesting thing is that there is another interesting bound, namely N equals 3D over 2 plus 3. Yes, and this bound, below this bound, we have only spheres. So here we have only spheres. We cannot triangulate anything with non-trivial topology. Sphere is trivial topology, the simplest possible topology for a D-dimensional manifold. We cannot triangulate anything with not sphere topology with smaller number of vertices than 3d over 2 plus 3. So this bound is so they claim that if we have smaller number of vertices, then it is sphere. This is a result by Brehm and Kühnel, 1987. Somewhat later, I will explain why. It is very easy reason why why this bound is as a. No, for two-dimensional torus, I should have 7 vertices at least, but the boundary is 6, and 6 vertices are enough for two-dimensional real projective plane. But for torus, you need at least 7. Yeah, for something non-trivial, well, but this is only the first part of the theorem. The second part says about what is on this critical line. So assume that we have exactly as much vertices. And it turns out that, first of all, there are only 4 possible dimensions. These are 2, 4, 8, and 16. So yes, well, yes. I'm sorry. I mean that either. So suppose that we have as much vertices and not a sphere. Of course, we have plenty of triangulations of spheres with such number of, but assume that it is not a sphere, then dimension is one of these numbers. So we have, I just would like to point out these points exactly. We have point 2, 6. So two-dimensional with 6 vertices. We have point 4, 9, 4-dimensional with 9 vertices, 8, 15, and sorry. And the last one is 16, 27. So only 4 possibilities. And moreover, in this situation, the topology of manifold is very much restricted. Namely, in this situation, our manifold, so first, it is the dimension. Second, our manifold, let M be that manifold which is triangulated, it is called a manifold like a projective plane. Is like a projective plane. This is the terminology introduced by Ilse and Kuiper in 1950s, and this means that this manifold admits a Morse function with exactly 3 critical points. So just these words means that M admits a Morse function with exactly 3 critical points. Well, sphere admits a Morse function with 2 critical points, and no other manifold admits a Morse function with 2 critical points. I must be careful here. I should say here a PL Morse function, and I don't want to specify exactly what does it mean, but the matter is that no smooth structure at all. I don't have any smooth structure, but okay. And this is the next situation. So the next situation, of course, each of the projective plane. What are projective plane? We have RP2 in dimension 2. We have CP2 of dimensions 4. We have HP2 of dimension 8, and we have octonionic projective plane of dimension 16. We have these 4 manifolds. Each of them admits a Morse function with exactly 3 critical points. But it turns out that at least here we have no other possibilities. Only this manifold admits. But at least here we have there are other manifolds which are very similar to those two, but nevertheless they are not they are not homeomorphic to them. So there are other manifolds with Morse function. In all three cases, they must be different, pairwise different real numbers. Where x, y, z are coordinates which are normalized so that their sum of squares is 1. And if these three numbers are pairwise different, then you have then this function has exactly three critical points. These are 1, 0, 0, 0, 1, 0, and 0, 0, 1. These three critical points. And obviously, if we have exactly three critical points, then one of them is global minimum, one of them is global maximum, and the second has index with exactly half dimension. Because of the Poincare duality, it cannot have other index. So at least, for instance, well, a result when a result which follows from Adam's theorem on Hopf invariant 1, that such manifolds exist only manifolds which admit such Morse function with exactly three critical points. They can exist only in these 4 dimensions. So in other dimensions there are no manifolds with which admit such Morse function. Yes, with the smallest lambda it is minimum, with this largest it is maximum, and the third one has index exactly in d over 2. So we have at least such manifold. For instance, immediate consequences of this condition is that this manifold admits CW decomposition with exactly 3 cells. And these 3 cells are, of course, 0-dimensional, d over 2-dimensional, and d-dimensional. Of course, if d is not equal to 2, then this implies that, for instance, homology of this manifold, cohomology, are as they should be for a manifold with 3 cells. So it is where degree of u is d over 2. So the manifold must be very similar to these manifolds, but there are other manifolds with this situation. The most intriguing situation is in dimension 4. In dimension 4, we do not know whether there are other manifolds which are like projective plane. And this is a problem which is very similar. This is more or less a problem on existence of non-standard smooth structures on CP2. And this is very hard problem. Now nobody knows about existence of of exotic smooth structures on 4-dimensional sphere or CP2 or something like that. So in dimension 4, if any other such manifolds exist, then they are homeomorphic to CP2, but they can be not diffeomorphic, so or not PL homeomorphic. Okay, so there are such results about manifolds like a projective plane, but I am interested mostly not in these manifolds. I am interested in these triangulations with critical numbers of vertices. And what is known about these triangulations? Up to very recently, up to my work, before my work, which I am talking about, there were exactly 5 examples of manifolds with this number of vertices. Namely, I just would like to list. First example is we have RP2 with 6 vertices. This is a very nice object. Just you can take the boundary of the icosahedron. Icosahedron is a regular polytope with 12 vertices, those which consist of triangles. Not the dodecahedron of pentagons and icosahedron of triangles. So, and you take the boundary of this icosahedron and take the quotient by the antipodal involution. You get 6 vertices out. There were 12 vertices, so you get 6 vertices, and this is RP2 topologically. One can ask why icosahedron, why we cannot take, for instance, octahedron? Because if we take octahedron, we get not a simplicial complex. We get such problems. But for icosahedron, this is a true simplicial complex. So this is the simplest triangulation, which is not a sphere. It is unique. So this is the only triangulation of with 6 vertices, which is not a sphere. And just I would like to write down that its symmetry group is the alternating group. Well, it is not surprising since it comes from icosahedron. We have the group A5. Yes, this is the first point. So in this first point, we have exactly 1 example, and there are no other. Well, the second point. The second point is CP2 with 9 vertices. This triangulation was constructed by Kuhnel in 1980s, something like 1983. Okay. It is a rather nice triangulation. It can be described more or less explicitly. Okay, and we again have uniqueness. So there is theorem that this is the only triangulation with 9 vertices, which is not a sphere. And the symmetry group here has order 54, and this is a group by Cn. I denote the cyclic group of order n. So we have C3 squared and semi-direct product by C6. So such some group of such kind. Okay. The third point. Is 8-dimensional manifold with 15 vertices. Here we have HP2 with 15 vertices. And here the story is as follows. The situation is as follows. In the late 1980s, about 1987, Brehm and Kuhnel constructed 3 examples of such three different examples of such triangulations. And they wrote preprint that they constructed three triangulations of this. I saw this preprint of this manifold. Here are triangulations, so they just list simplices, so everything is okay. But then for 5 years, this preprint was not published. And the reason is very simple. They were asked whether they can prove that their manifold is indeed HP215, HP2. Okay, so they have a simplicial complex with 15 vertices, and assume that you have explicit simplicial complex of dimension 8 with 15 vertices, and you are interested in whether it is HP2 or not. How can you construct a homeomorphism? I can't imagine how to construct homeomorphism between 8-dimensional objects of completely different nature. One is smooth manifold, and another is simplicial complex. It is problem which, well, it is completely unknown how to solve it. They tried several approaches, and finally, yes, yes, but it is immediate from their general theorem. So if it is easy to see that it is not a sphere, it has Euler characteristic 3. So this is not a sphere, hence this is a manifold like a projective plane, and so on and so forth. So it has homology and so on. It is simply connected, no problem. So its topology is very close to HP2, but finally in 1992 they published a paper where they say that they constructed 3 manifolds with 15 vertices which are like quaternionic projective plane. So that they couldn't prove that they're HP2, and this problem remained open for many years, and finally in 2016 Denis Gorotkov, so they constructed these examples, but he proved that this is indeed HP2, that they proved that they are HP2. Well, the matter is that for such manifolds, there is classification theorem, and they are known to be distinguished in dimension 8. They are known to be distinguished by their Pantryagin classes. So actually, to prove that, since we already know that this is a manifold like a projective plane, it was enough to show that the Pantryagin class of this manifold is as it should be. The first Pantryagin class is the same as for HP2. And Denis computed the Pantryagin class of this manifold using my combinatorial formula, and this yielded the result. So, okay, this is the story. And last combinatorial part, that these 3 triangulations, they appear homeomorphic to each other. So from topological point of view, they are the same, but from combinatorial point of view, they are different. So they are not an isomorphic, and their symmetry groups, for the most symmetric of them, has symmetry group A5. Again, here it is much less obvious, so it is some strange fact that we have A5 here. Other 2 have smaller symmetry groups, namely A4 and S3. So we have 3 examples with such symmetry groups. Okay, for icosahedron, we know that its symmetry, its orientation preserving symmetries are binary icosahedron groups. This is a standard fact, that this is its symmetry Its orientation preserving symmetries are just A5. So they just when you pass to quotient, the symmetry group preserves. So it is not hard that here, but here it is very interesting that combinatorially this situation is related to the outer automorphism of S6. Namely, how to see the action of A5 on 15 vertices. Well, we have natural action of S6 on the set of 15 points. Namely, S6 acts, of course, on the set 1 from 1 to 6. But now we can take two-element subsets. And there are 15 two-element subsets. So S6 acts on 15 two-element subsets of this set. And this is action of S6 on 15 points. Now for A5, we have natural inclusion. A5 is contained in S5 and is contained in S6. So of course A5 acts on these 15 points, but this is not the action we need. The right action is obtained if we here use the outer automorphism of S6. That's SL2 over 5?
Yeah,
well,
just right over
SL2 over 5 is not A5, but it's a binary hexahedral group. So yeah, so of course this is very close to SL2. PSL2 over 5, yeah. Yes, of course, this is PSL2 over 5, and yes, you can look from this point of as well. Yeah. This Pentragian number is 2. Not Pentragian number, Pentragian class is 2 multiplied by the generator. So P1 is 2 multiplied by generator. Okay, maybe later I return to.
Small question. How
yes.
many orbits do we have in the set of vertices?
One orbit. This is the yes. Yeah. Well. Yes. Yes. In this, this is a good question. Thank you very much. In this situation, these 3 are vertex transitive. The action is transitive on vertices. Here and here it is not. Well, okay. So we have 5 examples. Well, and here we do not have a result of uniqueness. So here we do not know. Maybe there are more triangulations which we do not know. So in these 2 situations, it is proved that these are only 2 examples. Only one example here and one example here, and there are no other examples. But in this situation, we do not know whether these 3 examples are all possible examples, or maybe there are other. Well, and moreover, nothing was known about this last point. Well, and this is what I'm going to tell about. Well, now I would like to formulate my result. Nobody knows This is just no other examples are known, but maybe there are other examples. It is not proved that there are, so it is unknown. I think now I would like to formulate the result for 16-dimensional case, and we see that it is so strange that I can hardly say anything about expectations. Well, I have several expectations also. Okay, so what is in the case of d equals 16? Nothing was known, but now I have examples, and this is what I want to say. So, theorem that in dimension 16 we have there are at least so I would like to say about 27 vertex 16 manifolds, of course, which are not spheres. There are plenty of spheres, so I would like to consider such manifolds, well, which are not spheres. And there are at least, well, at least as many such manifolds. I'm sorry for this, but yes, this is an answer of a question about expectation as +2. Well, this is approximately 1.3 times 10 to the power 103. So we have at least as many pairwise non-isomorphic triangulations of such kind. Yes, yes, yes. This is an integer. It actually divides by 300. So there are at least as many such triangulations, which are pairwise non-isomorphic. So the situation is as follows. Well, and now I am in the same situation as Brehm and Kuhnel were in 1980s. So I do not know whether these manifolds are homeomorphic to the octonionic projective plane, or they are just manifolds which are like octonionic projective plane. I will say maybe somewhat later some topological things, but here we need to compute the second pentagon class. Yes. Which are not spheres, so they are manifolds like no. Actually, the situation is as follows. This is one big, well, all these triangulations, I do not know whether they are OP2 or not, but at least I know that they are PL homeomorphic to each other. This is the same manifold. Topologically, this is the same manifold. Combinatorially, they are different. But topologically, these are the same. And about these two, I do not know. Maybe they are different from them. Maybe they are also PL homeomorphic. I do not know. And I do not know whether at least one of them is homeomorphic to the octonionic projective plane. No, well, the second pentagon class is 6 multiplied by the generator of the middle cohomology group. The isometry group of the octonionic projective plane, I will come to this. It's the exceptional Lie group F4. So isometry of the octonionic projective plane is F4. Well, and the situation is as follows. Why such huge number? I prefer to start with this, and then I explain. Well, namely, there are 4 triangulations with which are the most symmetric, with the best known for me symmetry group. Well, so there are 4 examples: K1, K2, K3, and K4, which have symmetry group of order of this order, 351. And this symmetry group is C3 cubed semi-direct product with C13. Well, I prefer to think about it as it is convenient to think in the following way. This is we should consider a field of 27 element, and we have its additive group, and we have its multiplicative group. Its multiplicative group is a cyclic group of order 26, but I take only half of them, namely I take the group of all squares. So, and of course we have this natural, this is multiplicative group, and I take squares of it, and so I take all transformations of the field of 27 numbers where A is square. Well, okay, a squared x plus b. They form a group of this, and they naturally act on the set of 27 elements.
It does not have the set of the
You want to say that
yeah.
This is a field of 27. This no, not Z27. This is field of so additive group is isomorphic to this one.
In the left-hand side,
Factors of 3, and the left hand side has only 3 factors of 3. I mean, the left hand side is 9 times 13 of order.
No. C3 cubed. So additive group of the field of 27. Yes, I mean the subgroup consisting of squares. Yeah. I'm sorry. Yes. Well. Okay. This means subgroup consisting of squares. Yes. Well. Okay, which is squares squares in F27. Okay. Okay. Well, the situation is that we have four triangulations, exactly four triangulations with this symmetry group. I will explain later why we have four triangulations. No, well, not explain, but I will actually, this result is highly computer assisted. So actually, I will explain what is the algorithm which yielded these four examples being implemented on computer. So I cannot construct them by hands. I will show what are their sizes to explain why I cannot construct them by hands. But now the situation is as follows. In all these cases, except for the first one, in case CP2 and in this case, the following a very nice situation occurs, namely, well, assume that you have a triangulation of a manifold. Let us forget for a moment about that particular examples, but just any triangulation of a manifold. And it may happen, well, for each simplex, you have link of this simplex. These are, you can take the star of simplex, so all simplexes that contain this particular simplex sigma, well, delta, for instance, and this star of delta is always the join of delta with link of delta. So this is such around this, the triangulation which we see around this simplex, and it may happen that the link of a simplex is the boundary of a simplex. It is very special situation, but assume that we have such situation. So assume that we have the situation that the link of some simplex is the boundary of another simplex. It is very special situation, but then our triangulation has a subcomplex consisting, which is the join of a simplex and the boundary of a simplex. I just would like to point out the first case. Well, if you have one-dimensional simplex and its link is the boundary of one-dimensional simplex, this is like that. Well, this is one-dimensional simplex, and its link is 2 points, which are the boundary of another one-dimensional simplex. And if you have this situation, then you can perform such move. You can delete this subcomplex and replace it with the subcomplex like that. You take the boundary of the first simplex times join with the second simplex. So you see situation like that. This is the simplest case where simplexes are one-dimensional, but in general case, okay. Yes, this can happen for multi-dimensional as well. Yes, this is called flip. Well, but the situation is as follows. This operation is good only if this simplex was not in the initial triangulation. If these two vertices were already connected by an edge, then you cannot make this flip, since you get two simplexes with the same, which is prohibited. So we should always check some conditions. But it turns out that there is very nice situation when you should not check anything. Namely, look, in all these 3 cases, and in all these 4 cases, 6, 9, 15, and 27, the number of vertices is divisible by 3. So let the number of vertices be 3m, where m is 2, 3, 5, and 9 in this situation. And assume that all vertices are decomposed into 3 groups of m vertices. These will be the simplex delta 1, the simplex spanned by these vertices. This will be the simplex delta 2, and this will be the simplex delta 3. And assume that there are the following subcomplex. That the link of delta 1 is the boundary of delta 2. The link of delta 2 is the boundary of delta 3. And the link of delta 3 is the boundary of delta 1. It seems that this is a very special situation, very, very special situation. But if such situation occurs, then one can always do the flip like that. This triple flip, so three flips to get immediately, and one can check that nothing bad occurs. Okay, simplex delta 2 appears here, but it disappears here. So totally everything is okay. Oh, sorry. Yeah. Well, and it turns out this is some very strange fact, but in all these situations, in this, and in this, there is subcomplex of such kind. So no, not only one. Well, the situation is as follows. In the case of RP6, there are plenty of such subcomplex. I don't remember how many, but but all of them are isomorphic to each other. If you perform any of these triple flips, you again get the triangulation which is isomorphic to the same RP6. So nothing new. In this case, there is only one such subcomplex. If you perform this triple flip, then the obtained subcomplex is again isomorphic to the initial one, and we again get nothing new. Here, Brehm and Kühnel, in fact, originally constructed this one, the most symmetric example. Further, they found that this example contains a subcomplex of this kind, but not one. It is one up to the symmetry group. But we have symmetry group A5, and it turns out that there are, in this case, in the case of HP2 15, there are exactly 5 subcomplexes. The A5 acts on them, and this orbit consists of 5 subcomplexes. There is one orbit consisting of 5 subcomplexes. We have these 5 subcomplexes. A5 acts on 5 elements in the standard way. And it turns out that if you perform all these triple flips, well, these subcomplexes do not intersect each other. More precisely, their interiors do not intersect each other. If you perform all the 5 triple flips together, you get the same manifold. This is some surprising, but this is true. If you get, yes, yeah, isomorph. It is isomorph. Yeah. If you perform all 5, then you get an isomorphic triangulation. If you perform either only one of them or only 4 of them, and it doesn't matter which one or which 4, you get this second example. And if you perform either 2 of them or 3 of them, then you get the third example. So the situation is like that. And what happens in the situation of dimension 16? If you consider this K2, this is my enumeration. There are, I understand that at the moment these 4K do not distinguish, are not distinguished from each other, but one of them I denote by K2, and this K2 also contains subcomplex of such form. And again, this subcomplex is unique up to the symmetry group. Symmetry group is this. No. K. This I said that there are four pairwise non-isomorphic triangulations with this symmetry group. I take one of them. Well, just don't ask me why it is K2. I take one of them, and it turns out that this triangulation contains a subcomplex of this form. Moreover, contains exactly one orbit of subcomplexes of such kind, orbit with respect to the symmetry group. But now the symmetry group acts transitively, acts freely on these subcomplexes. So we in fact have 351 subcomplexes, which are their interiors are pairwise disjoint, so we can perform these triple flips independently of each other. Well, and so now, so these 351 they form orbit with respect to this symmetry group, so they can be naturally identified with this group, numbered by elements of this group, up to the same left shift. So, and if you perform any, well, you can perform any, you can choose any subset of this group, and there are 2 to the power 351 of such subsets. You can perform these flips, and you always get different triangulations, except for the common left shift. So you get something about something like that, and this is because some subsets are invariant with respect to some shifts. So this is some combinatorial computation, but generally this is the number of subsets of this group up to left shifts, and there are as many triangulations. Well, some of the subsets have non-trivial stabilizers. You get you should divide not by 351, but by some smaller numbers for some of them. Last, yes. The last funny situation is that if we perform all 351 triple flips, then we get K3. So if you perform all, then the symmetry group is preserved. Well, and here we have phenomenon which did not exist before in all these examples. For these two triangulations, we do not have any such subcomplex. So unfortunately, this method doesn't work at all. So these are +2, and I cannot get more out of them. Okay. So this is the description. Yeah, thank you very much. Yes, all things which I say, they they should be proved, and they have been proved, but I just formulate the result. So it is not so easy situation to prove that all these triangulations are pairwise non-isomorphic. Well, the idea is about roughly speaking, the idea is as follows. These the simplices which enter such subcomplexes, they are different from simplices which do not enter such subcomplexes. We can easily easily distinguish them by some numerical numbers of neighbors and so on. I don't want to go in details, but we can distinguish them. So any let us take this K2 and remove from it these 3, 5, 1 subcomplexes. So you get some complex J, which is not a manifold, but just some subcomplex. And I can consider its symmetry group. And its symmetry group is, again, this one. So we cannot have any additional symmetries. If we have any non-trivial symmetries, then it also would be symmetry of this J. But we cannot have this. Well, so this is roughly some. Well, what's time? I'm sorry.
6.
Okay. So in the now I would like to say some words about how this was proved, how this was what is the answer? I actually, these 4 are given just explicitly. I can list their simplices, their maximal simplices, but and I can point out this subcomplex and one of them, and so I have its orbit. So I of course I cannot list simplices for all of them by trivial reasons, but for if one asks me for any of them corresponding to particular subset, I immediately can produce the list of its simplices. So now I would like to say, yes, I have conjecture, natural conjecture, that these are octonionic projective plane. That all these triangulations are PL homeomorphic to the octonionic projective plane. Actually, my expectation is that it should be true, but actually, I have I have such expectations. Another expectation. I would not be surprised if it is true for these, but it is not true for this too. Maybe I wouldn't be I would be very surprised if it is not true for this plane of triangulations. Of course, it should be symmetric situation. We should have this good manifold, not some strange manifold similar to it. Well, okay, maybe now I would like to come. Well, first of all, I would like to point out what are the numbers of simplices with which we need to work. And also, I would like to mention one very important combinatorial property of such triangulations. In fact, I have not formulated this theorem by Brehm and Kümmel in full its form. Now I would like to add something. Namely, they proved that if such triangulation exists, at the moment they didn't know examples for OP2, but they proved the following: if such triangulation exists, then it should satisfy complementarity condition. Complementarity condition is the condition like that. Assume that you have, you have n vertices, where n is 6, 9, 15, or 27. Yes? you have this n vertices. I just number it from 1 to n, but it doesn't matter how to number them. Just and well, just maybe this is. I will identify any simplex with its set of vertices. I am conveniently speak on such combinatorial language, so I say that, well, edge is two vertices and so on. So if we take any subset of this V, then exactly one of the two sets, exactly one of you can take S and you can take the complement of S. Exactly one of them is simplex. So it is a very funny, a very nice condition that so out for each two complementary subsets, well, this is property. This is property of all examples, not only of constructed. They prove that if you have such triangulation, then it satisfies such condition. So of all examples are, of course, also satisfied. And this in particular means, if, well, no. I explain why it is so. Well, and actually to explain, I would like to prove why this bound holds. Now some topology. Well, assume that you have manifold with several vertices. You can do as follows. You can use a Morse-like process. You can add vertices one by one and consider subcomplexes spanned by these vertices, and consider the topology of these subcomplexes. Let us do it, but with one restriction. I number vertices so that the last d+1, the highest d+1, span a simplex. Well, my triangulation has at least one simplex. So I take there are d+1 vertices which are simplex, and I have n minus d minus 1 vertices, which are all other vertices. So I have, when I take the first, here I have some simplexes, some non-simplexes. So here I have some subcomplex on this number of vertices. Well, when I on this level, so I consider this subcomplex, it has some topology. It has several homology groups. What happens when I add this simplex? I add this simplex and all simplexes from here to here. It is not hard to see that homotopically, I just add one cell. Homotopically, this is attaching a cell. Passing from this subcomplex, L to the whole manifold is attaching one d-dimensional cell. I don't know. Just it is not a manifold. It has no boundary. I take all simplexes which are contained here. It is some subcomplex, but attaching this one from homotopy. Yeah, everything is compact. Yeah. All vertices are here. Yeah. Yes, and adding this and all medial is at. Yes, it's a process of. Yes. But homotopically, it's attaching a cell. No. No, sorry. This is not just taking one simplex from the complex. I remove this simplex and I remove all simplexes which have at least one vertex here. And when I add them all together, from homotopy point of view, this is only at HNSL. I'm so sorry. Well, and I don't know anything about topology of this one, but at least I know, okay, if it has such many vertices, then it cannot have homology. All its homology, all homology is in dimensions less than or equal this minus 2. I cannot have homology. This complex is too small to have homology in high dimensions. So all homology is in the dimensions less than or equal to this one. Well, and now I add one cell. So I add one homology Z to homology group to the highest homology group. But I cannot add anything to the intermediate homology group. But now I have Poincare duality. So I must have, if this is not a sphere, then I have homology in some, I have at least some non-trivial homology in between. But then I should have this homology beyond the half of dimension. And this estimate, well, it is not hard to write down that it is exactly that estimate that you have. It is obvious that we should have about d over 2 vertices here. If we be precise, then we get exactly that bound. But why this equality can happen only if we cannot improve this bound. So in the case of n equals 3d over 2 plus 3, well, here we have d plus 1 vertices. So here we have exactly d over 2 plus 2. And this must be the boundary of a sphere, the boundary of a simplex. This is the only way to have homology in this particular dimension. Otherwise, we can improve bound by 1, and we again come to a contradiction. So the only way is that the complement of the simplex is a non-simplex. So we have here the boundary of a simplex. So this is more or less, this is not an exact proof, but this is an idea of proof why this complementarity must be. So we have this complementarity condition. What does it mean? First of all, it means that we have huge number of simplices. Namely, well, okay, out of each 2 subsets, exactly 1 is a simplex. So to be precise, in 16-dimensional situation, we have 2 to the power 26 minus 1 simplices. This is the number of simplices in any candidate to be such triangulation. This is, of course, the number of simplices of all dimensions. Now, it is not hard combinatorial. Well, one has such so-called dense Merville relations among numbers of simplices of different dimensions. One has this complementarity condition, and one has that the Euler characteristic must be 3. And all these equations together yield just combinatorially that actually we know the F vector. We know what should be the numbers of vertices, edges, and so on for any example if it exists. So even before my result, nobody knows examples. But if examples existed, then their number of vertices, edges, and so on must be as well. I can write it down, but I don't want. So the number of vertices 27, the number of edges 351. Actually, up to well, since the complex is 16-dimensional, any simplex contains not more than 17 vertices. So this complementarity says that any set of 10 or less vertices is a simplex. So in particular, you have such, it is called, I'm sorry, I forget in English, in Russian, смежностность, I forget just. No. In another word, neighborliness. It's called neighborliness. So and the number of maximal simplices is like that. So the number of maximal simplices must be like that, and we see that already this number is large enough to work with it. And if we try to find different, all possible. So if we don't want just to consider an example which somebody presents to us, but if we would like to find out for examples, then you need to find out for collection of so many simplices. So it is hard enough. But now the idea is okay. The idea was that since we have these examples and we see that here we have good symmetry, large enough symmetry groups. The idea was that here we also expect to have some symmetry groups. The next question, which symmetry groups do we expect to have? Actually, the expectation was wrong. I discussed this situation with several people, with Dmitry Orlov and with Sasha Kuznetsov, and the idea was that the group must be related. The group seems to be related to Weyl group of type E6. So I tried first some. Where is E6? I forget to say an interesting situation. There are so-called Severi varieties. Now, forget for a moment about triangulations, and let us consider a nice question in complex projective algebraic geometry. So assume that you have a I prefer to have n-1 here. Projective space, complex projective space of dimension n-1, and we consider X, which is d-dimensional, irreducible, smooth projective variety. And starting from this variety, one can consider the second variety of this X, which is, by definition, we take all pairs of points of X, we take all seconds, all lines through 2 points in X, and we take the union of all these lines, and we take the Zariski closure, and we get some submanifold. And we can ask whether this submanifold, we obtain some variety. We may ask whether this variety is the whole projective space, or maybe not. Well, yes, I forget one condition. Suppose that this variety is not contained in the hyperplane, not contained in hyperplane. So, and then there is a theorem by Zak. It's 1980s. And theorem is as follows. Assume that n is less than or equal to 3d over 2 plus 3. Then the second variety is the whole projective space. Assume that, this is the first part. Second, assume that n equals to 3d over 2 plus 3. Then either the second variety equals the whole projective plane space, or d is one of the numbers 2, 4, 8, and 16. And here we have exactly 4 examples. We have Veronese surface P2 to P5. We have Segre embedding P2 times P2 to P8. We have Plücker embedding Grassmannian 2,6 into P14. And we have some special variety, which is related, it is called Lazarsfeld variety, and it is related to E6. And yeah, homogeneous variety by certain special parabolic subgroup. I don't remember which one of them, but so, and there are actually, this is natural analogy, but this analogy comes further. Either second variety is the whole, or it is smaller only in 4 cases. You have only 4 counterexamples when it is not the whole. And here, well, it's very much parallel to this situation. No, here you have exactly 4 examples. And this is theorem by Zak. This parallel was noticed by such mathematicians Chapaton and Manivel. They wrote a paper where they explored this, numerically explored this parallel further. Namely, they noticed that, I put dots here, but there are some numbers, some precise numbers, that these numbers are dimensions of certain representations of groups which are naturally related to these homogeneous varieties, or in this case, this is E6 and so on. So yeah, this is, for instance, dimension of representation of E6, and so on and so forth. So there are some parallels which nobody understands. So they are just mentioned, and it is not clear what to do with it. So my expectation after some discussions with different people was to find out some group related to Weyl group of type E6. Well, actually, my idea was actually my approach was that was to use complementarity to start computer algorithm. To start computer algorithm, if I know the symmetry group, assume that I have a group G, which acts on this 27 vertices. I now want to be precise. I have 27 vertices, and I have a group of permutations of these 27 vertices. Well, the idea is the problem is not to point out an algorithm in the sense of mathematical logic or something like that. My goal is to obtain an algorithm which will work indeed in reasonable time, implemented on some reasonable data. And finally, I used this algorithm for this particular group of order 351, and it works for 7.5 hours. On my usual laptop, not on some. But for instance, if you take the situation is very thin, so the same algorithm did not work on groups of order about 100. It didn't work at all. It becomes completely complicated. So it is some balance between number of size of group and so on. So what is the idea? The idea is, okay, you have I would like to think only about maximal simplices. And I don't want, at the moment, I don't want my subcomplex to be a manifold. I just want to check that this subcomplex is a pseudo-manifold. This means the following, that if I have two maximal simplices, 16-dimensional simplices, I would like it to be 16-dimensional pseudo-manifold. Then if you have to each 15-dimensional simplex, there are exactly two adjacent 16-dimensional simplices. This is pseudo-manifold, and I can have arbitrary singularities at smaller codimension and at higher codimension. So the idea was as follows: I just take all 17 element subsets of the set of 27 elements. Okay, so I have the following number of them. But if I have a symmetry group, so if I have, for instance, that particular symmetry group, then I have about this number of orbits. So this is the number of all subsets. This is the number of orbits. If I'm looking for symmetric triangulation, so I should either take the whole orbit or not take the whole orbit to my triangulation. So I have as much orbits, and this is in this particular case, this is the following number. It is still too huge, so it is a rather big number of orbits. I cannot. So finally, this number divided by 351 is 286. So finally, I should take 286 out of as many simplices, orbits of simplices, to obtain a pseudo-manifold. Of course, I cannot do it just straightforwardly, but I can do the following. I can start first of all, some of these simplices are inappropriate from the very beginning. Look, I prefer to speak not about simplices. Okay, let us speak about simplices. Assume that I have a simplex. This simplex has 17 vertices. And I act, this is sigma, and I take the simplex G sigma for some element of symmetry group. Assume that their union is the whole set of 27 elements. So it can sometimes happen that the union of I take subset, I act by a group element, I take another subset, their subsets, each of them consists of 17 elements, but maybe their union is the whole set of 27 elements. If such thing happens, then the sigma should be prohibited. Why? Because I have complementarity, and I know that the complement is not a simplex, so it cannot, the complement of sigma is not a simplex, and it cannot be contained in another maximal simplex. But if sigma is a simplex, then G sigma is also a simplex. And then the complement of sigma is, well, they necessarily intersect. They have 17 vertices each. It is a simplex. It is not a maximal simplex, but it is a simplex. No, any subset of a simplex is a simplex. So all such sigma must be prohibited. Also, there is another reason why simplices must be prohibited. Namely, look, assume that I have a simplex which consists of 17 points, and assume that I can find another two simplices in the same orbit, so that the intersection is consists of 16 points. If such situation happens, then I also must prohibit this sigma, because together they give me three simplices which have the same, could I mention, one face. If such situation, then this is another way to prohibit. So again, so there are two ways why I should prohibit simplices. If in this particular situation I have so many number of orbits, and I have admissible orbits which are not prohibited by these two methods. The number of admissible orbits in this situation is, of course, this cannot be done by hands, but everything I explained so far is made on computer rather fast. So there are as many admissible orbits. But this is well, this is very small progress. It is not as good as one can expect. But it turns out that there are a lot of now. I would like to introduce such things as prohibitions and requirements. Some simplices prohibit other, and some simplices require other. What does it mean? Some orbits of orbits. Well, assume that I have here one simplex and here another simplex. If I have situation like that, then, well, sigma 1 can be in my triangulation, and sigma 2 can be, but they cannot be together. So sigma 1 prohibits sigma 2, and sigma 2 prohibits sigma 1. And sometimes also some requirements appear. Well, for instance, assume that you have this simplex sigma 1, and among all subsets that contain this subset, all but one are prohibited so far. So then, of course, the sigma 1 requires to add this. And it turns out that we can improve our knowledge of requirements and prohibitions, so that running through all simplices, we obtain some knowledge. We knew that some simplices, some orbits require other. We knew that some orbits prohibit other, and then we just try to take some orbit and to improve our knowledge. And it turns out that very soon we come to a contradiction. Well, it turns out that once we take one orbit, we have so much knowledge about these prohibitions and requirements that rather soon, if this orbit is not in in a triangulation. Then rather soon we came to a contradiction, and we throw this orbit away, and then we again improve our knowledge since some. So this is the general plan. Then there are some not mathematical but just heuristic moments of, for instance, which simplex to take. It doesn't matter mathematically, but from it turns out that if we take just arbitrary simplex, the program works. I couldn't wait for its working, but we have some heuristic which simplex to take first. This heuristic doesn't mean that we still the program finds all pseudo-manifolds with the given number of vertices, complementarity, and the given symmetry groups. But this is just heuristic which orbits to try first. It still tries all of them, but in some order, and this influences the running time very much. Well, so the answer is this. The answer is the list of 286 maximal simplices. Unfortunately, I cannot put any order in this. 286 is enough small to look on this. I can print it on the. So I have it pre-printed, and I can look on this list of simplices. But unfortunately, I cannot do anything with this set of simplices by hands. So if this algorithm is implemented for this particular group, then the result is it produces 24 candidates. It produces 24 pseudo-manifolds. So the result is that for this vertex of 27, for this now set of 27 elements, and for this particular group of order 351, there are exactly 24 pseudo-manifolds which satisfy complementarity, are invariant about this group, and satisfy complementarity, and has correct number of this number of maximal simplices. There are also plenty of examples which has smaller number of maximal simplices. These branches of algorithm should be cut once we have smaller number of simplices. We just don't consider this because there are plenty of such examples. So we have exactly 24 candidates with this symmetry group, and it turns out that all of them, first of all of them are PL manifolds, and this is also a rather non-trivial statement. The matter is, okay, there are plenty of standard programs which, for instance, simplify some complexes by means of flips and find out whether these complexes are spheres or not. When I obtained these 24 candidates, first I hoped to use one of these standard methods. It turned out that none of this program allows to download into it the complex of this size. Not only it does not work on it, it even doesn't allow the entry of the initial data of such size. I don't have time for this, but there is some, I introduced some very special methods which work properly. It is based on such concept of non-evasiveness of complexes, which works only in this situation, but it works in this situation. And all these pseudo-manifolds are PL manifolds. So why there are 24 here and only 4 here? The matter is that if we consider this particular group as a subgroup of S27, then its normalizer, then it has a normalizer. Its normalizer, of course, the group is contained in its normalizer. Well, sorry. Well, of course, it's normal. It's I'm sorry, and it has index 6. Why? I can easily point out 2 elements of this normalizer. First of all, this group consists of multiplication by squares and addition plus b. So I have a multiplication by non-square. For instance, it does not, for instance, by -1. It doesn't belong to the group, but it, of course, normalizes the group. And second, we have a Frobenius automorphism. The Frobenius automorphism. So we have normalizer. The group has index 6 in its normalizer, and the quotient, of course, acts on the set of these 24 pseudo-manifolds. So these 24 pseudo-manifolds decompose into 4 groups, and the 6 manifolds in each group are isomorphic to each other. But the manifolds in different groups are not isomorphic to each other. This is also not so easy. The idea is that, okay, they have the same F vector. They have the same F vector. They have the same numbers of simplices of all dimensions. So we cannot distinguish them by such numerics. But we can distinguish them by slightly more complicated numerics. Namely, we can consider for each 14-dimensional simplex, we can compute the number of 16-dimensional simplex round of it. This number varies from 3 to 9 in any of these simplices. But now the distribution of simplices with different numbers of neighbors is different in these 4 cases, so we can distinguish them by such numerics. Well, and then we can find for these special complexes, and it turns out that in these 2 situations we have no such complexes. In these 2 situations, they're connected by such complexes, and so on. Well, and maybe the last thing which I want to say is why this group is good group. Well, I have 2 answers. First, we see here 351, and this is divisible. So we have some ideas that maybe this is a good order of the group. But this is rather strange. Well, yeah. Well. Yes. Yes, of course. Well, the answer is as follows. For CP2, the algorithm works, of course. Even if we take the trivial symmetry group, we do not prescribe any symmetry group. We just say take trivial symmetry group. I can write it down. I'm sorry. I don't remember. It's 9, 36, 84, 90.
very innocent number. And why can't you put into the computer and just one possible outcome?
In CP2?
Yes.
Yes, of course can.
But then I don't know why you are saying that this is unknown thing.
No, no, no. The unknown case is not the combinatorial question. It's topological question, whether there exist. It is different question, whether there exist manifolds which are like the projective plane, or whether they can be triangulated with this number of vertices. They cannot. But maybe there are some exotic manifolds which cannot be triangulated with small number of vertices.
No, but I mean, these all possible outcomes.
Yes, in dimension 9, there is only one possible complex. The combinatorial question in dimension 4 is completely closed. The topological question is open. Whether there exist manifolds which are like the projective plane, but not a projective plane itself. If they exist, then they do not have such good triangulations, of course. It's only one way theorem. If you have triangulation with such number, then it is a manifold like a projective plane. If you have a manifold like a projective plane, there is no result that there is such triangulation. Okay, so why this group? This group actually I tried this. To be honest, I tried this group just by chance. So when I wrote a program, I tried those groups which seemed natural for me. I found no examples. The algorithm said me that there are no examples of manifolds with these groups. Then I just take it just without any reason. But if the group is too big, yes, if the group, then the algorithm doesn't work. Yes, and this group is in between. Well, and afterwards, finally, a posteriori, I see the reason why this group is rather natural. The matter is that there is a very important if you take the OP2 with standard Fubini-Studi metric, then, as I have already said, the isometry group is F4, the exceptional Lie group. Equals, yeah. Thank you. Equals F4, and in F4 there was a nice paper by Alexeyevsky. This is not Dmitry Alexeyevsky, but his brother Andrei Alexeyevsky. It's 1974, and he studied so-called Jordan subgroups of semi-simple of compact Lie groups. He also worked in a complex case, but for me the real case, the compact case is interesting. I don't want to give a precise definition what is meant by Jordan subgroup, but the matter, this is a finite abelian subgroup. This is not a precise definition, but only some part of it. But any Jordan subgroup is an finite abelian subgroup which is not contained in a torus. So of course, there are plenty of finite subgroups in any compact torus inside the semi-simple group, but there are some special abelian subgroups which are not contained in a torus. And in the situation of this F4, he found that, well, the only Jordan subgroup in his sense is T3 cubed, and so this group, if it is not contained in a torus, it should have finite normalizer. So, and its normalizer in F4 of this group is SL3 over F3. So he found this very well. Yes, yes. So one has such semi-direct product. Oh no, sorry. Normalizer is not. Normalizer is this one. SL3 of F3 is after taking quotient by the subgroup itself. So this one acts on this in the standard way, and you have such subgroup. This subgroup is too big to be. So it is natural to expect for symmetric group of a triangulation, those groups which arise as subgroups of isometry of the true OP2. So this subgroup itself is too large to expect that you have a triangulation with so large symmetry group. But of course, you have here an element of order 13, so you can consider subgroup of such kind inside it. So this is some. No, the action on vertices is the same. This is the only thing I. Yeah, I can place vertices very naturally on OP2. The next, OP2. Yes, I would not expect that it is possible. The complex is too huge. I would say some one thing which says that even easier things cannot be performed at the moment. OP2 with its natural Fubini 2D matrix, nature lives in 25-dimensional sphere. There is very natural isometric embedding. Well, and moreover, this OP2 lives here, and there is minus OP2, the antipodal OP2, and there is deformation retraction of the complement of one of them onto the second. So my expectation was at least, so here I have this OP2. Well, it's just some, I have vertices. I know how to place vertices. Then I can take straight simplices in S25, just usual spherical simplices.
Yeah.
And assume that these simplices do not intersect the minus OP2. Then at least, yeah, I can obtain a map of this simplicial complex onto OP2. And if I obtain such map, then most probably it will be a homotopy equivalence. It is not hard to prove that a map of complexes with so small homology groups is a homotopy equivalence. I expect that it is homotopy equivalence. And then I at least know that it is homotopy equivalent to OP2. Even this thing is not known. But I cannot prove even this simple fact that Well, I can consider all these simplices, but how can you prove that a simplex doesn't intersect a submanifold? Okay, you can prove it numerically. You must. It can come rather close. You should take a sufficiently dense net and compute this distances and see that these distances are greater than epsilon for a net, but it is completely impossible to take this on even on computer you should take it to 2086 times, and you should take, and it is okay, it is a small number, but you have here a rather large 16-dimensional spherical simplex, and you should introduce a net inside this simplex. I could not, I didn't manage to do this. I haven't managed to do this. So I even cannot understand that this subcomplex doesn't intersect something very simple. It is very far from trying to put any flow. I cannot do anything in this state. So, well,
maybe go into abstract all abstract all
maybe, but
Can you compute this second projection back?
well, no, I can't. No, there is no efficient formula for the second quadratic class. There are only for the first one. There are theoretical formula in the sense of pure algorithm theory. So I can provide an algorithm. This algorithm never works. The algorithm for an arbitrary quadratic class never works. It is so complicated, factorial of factorial and so on, that it cannot work. The reasonable algorithm is only for the first quadratic class. Well, actually, I could say something about topology, but I think that it would take too much time now. I think, yes, yeah, I finished it.